We're okay. All right, let's just review last time. And last time was just how to deal with the momentum operator. I know these last two lectures have been they've been a little stupid, really. But they're setting up. I mentioned that what we're doing today is kind of important. And we're also going to use it for some computational stuff. So hopefully you haven't forgotten your MATLAB because we're going to get back to some MATLAB, and some of the lessons today will be a big part of that. So here's just a little review. So all we really did was, okay, so I resolved an identity, and I'm praying you don't have to try. You should not have a problem with that. Okay, and I'm going to write this a little differently, mostly because that's what's in my notes. And if it's in my notes, I probably got it from the text. You know, the thing is a little, maybe I just need to be more careful, but how you write these integrals, what order, do you have the partial here, or do you have it in the back? And none of that is important, unless it confuses you, which means it's very important. But you can technically write these, you can put these things anywhere. Remember, partials are numbers. So numbers, they can't go outside the integral, can they? That's not true. Anyway, I'm just talking to myself. Okay, so notice I've done two resolutions of the identity. And the important thing here, again, this is really what we spent kind of really way too much time on, in my opinion. But we do need it. Is that, now I have to admit, I can't remember if it's x dash or double dash. My notes say it's x dash. Now this guy I'm pretty sure about. Left, right, in terms of x dash, double dash. But remember, it doesn't matter. This is zero. So you can arbitrarily, wipe out an integral. Hopefully you've gotten to really like direct alpha functions, right? These things are actually awesome. All right, no more integrals. So there you go. Really, all I've done is just set you up just for this. Remember, what happens is that the operator actually pops outside the inner product, and that's why it's really weird. And then, of course, I've got xx, which is a delta function. All right, so then you end up, and again, now we're kind of in vanilla land here. This hopefully becomes obvious. Here is the complex conjugate of a wave function psi beta. Let's call it psi beta. I can take just mention I can take constants outside. And again, this is an expression that is taught at an undergrad level. It's just an expectation value of momentum. And generally, pi alpha and beta would be the same state. So this would be the expectation value of momentum for, I don't know, cosine n pi x over L. Obviously, that's a part on the box. So look, there you go. That's all there is. Just to remind you, this is how you deal with momentum. I did want to point out, and I mentioned, I kind of ran out of time yesterday. I was going a little fast because we're feeling like we're a little behind. I just want to point out that there's this magical step I did, and it's faithfully reproduced from the book. Again, I know I've said this a zillion times, but the book is kind of absurd. Every now and then it's easier to understand. For the most part, I find it absurd. But I still hope you're reading along with it. Okay, so you recall that at one point in that big, the big derivation yesterday, Monday, was I did this. This is just one of the steps, and I said, oh, and then it turns into this. If you recall, this part got subtracted, and then this is where we figured out that the momentum has derivative inside of it. So anyway, and I mentioned to you, like, oh, I'll explain this. The book just does this. It doesn't explain it at all. And so a lot of people told me, they're like, well, what the heck? I mean, hopefully this isn't, this is the point a little bit left to the center of a wave function like I was drawing the other day. And here's this rather complicated expression. How the heck do you know that that's true? Where did that come from? Where's the identity or whatnot? And I was also like, yeah, what the heck is this? I just stared at it for a while, but now look at it. All right, now we know that the projection of a state into x is just a normal wave function like we learned at an undergrad. And then let's look at, okay, then I have the derivative of a wave function being pushed over by a certain quantity. Okay, so again, this thing is, I decided that there was knowledge of a wave function at a certain point, and this thing is just like, oh, well, yeah, and if you look a little bit to the left, I say that because minus dx. If you look a little to the left, if it was plus dx, I would have said right, but it's minus dx. So I said look a little left, and that's what the wave function is. So again, it's like kind of weird, but now look at this. Here's a point on the wave function. Okay, so I have a wave function, and I'm talking about a point. I know the derivative, and so I move left along the derivative a certain amount. You see what happened? It did the same thing. You simply approximated the wave function as a line, and you move down that line by a very infinitesimally small amount. It's just the wave function. It's just the wave function moved a little to the left because again, you go left because that's a minus sign. All right? See, it's the same thing. I don't know why the book doesn't explain that. It's really straightforward. Yeah? You're all okay? Right. A little funkiness there. All right, so let me just drop all this. I'm kind of reviewing it, wasting a lot of time. Okay, so we're going to get into something that is pretty important. And really, I blew the last two lectures just really built. The only thing that's really important about this is, I mean, I proved what the momentum operator is. That's quite an exercise. But today's, the thing I'm going to state today is going to come up again in this class. I'm going to do some computational work. But intellectually, it's really important. So we're going to do, we're going to definitely solidify this whole equality between momentum and space, right? So, yeah, just like I was just saying, right? Okay, so this is just a wave function like you've known it, and I've hinted to you for a long time that there's this thing too. I can write a wave function in terms of momentum, and this is what we're doing today, among others. And I'm telling you, nature doesn't see it any different. It's just a little harder for us to understand. Like a x ket is just a statement of a position, right? I can say that this is, I can pick a point in space, I'm just going to grab it, and GPS will tell me exactly where it is, elevation even. X, Y, Z, where is this point? This is what it's telling me. There's nothing else to really think about. That's just all it is. That's not really anything. In fact, it's such a nothing burger that there's not really much to think about. So you don't have too much of a hard time thinking about this, but now what about this? What about a ket with a P in it? What's a momentum ket? So we're going to cover this too. You can get a feel for it. Okay, well I can at least do this. Let's put a little dash. I think the book uses a dash. Again, it's just a placekeeping thing. So if I query the momentum of this momentum state, if I do this with x, you get knowledge of this. Hey, GPS, where am I pointing to? Well, you're pointing right there. Right? So what does momentum do with the momentum ket? Same thing. That was hopefully not too hard to follow. And I think I might be proving this, but as you can imagine, yeah, I'm going to do something with this later. A momentum ket projected into momentum is a direct delta function, a little funky. What else have I got? I can resolve an identity. I guess I should put a little dash. I don't know if the book put a dash there or not. I don't have a dash. Okay, that would be 1, so I can resolve an identity. And so, let's see, what else did I do? I could start with some arbitrary state. So let's, well, now okay, I've done this, but you know what I really should be doing is this. I should resolve an identity, right? So maybe I shouldn't have written that out quite like that. So there we go. And of course, we assume that the state is normalized. And so then, notice that I'm now going to project this into the bra alpha. And so what do I get? Alpha B, B alpha, which of course is, the reason I'm actually doing this, hopefully this is like, I don't know that I would need to tell you this. So actually, I just want to show you this. I got a symbol, I got a little symbol for a P wave function. So this might be useful to you. So you know I like to use psi, and put a little alpha there. Remember I got stuck a little bit about how do I want to put kets? Do I want to use psi for all the kets when the book uses a lot of alphas and gammas and betas? And so then I thought, oh, I'll put a little subscript. So for momentum, we're going to use, what is that?
5.
5, okay, 5. Are you sure?
Fire feed.
Fire feed. I don't know. It's that. That's what it is. It's called the that wave function. Okay. All right. Now our job today is how do we do this? All right. If nature sees them as the same, we really should be able to figure this out, right? Okay. So how do we do this? And it's actually kind of more fun. It's one of the more fun derivations. No attempt at a perfect mathematical proof with one approximation, which got me all pissed off last time on how that works. But anyway, okay, so what do we do? All right, so let me go back here. I'm going to rewrite it again so that I can kind of just keep working down. So I'm just resolving an identity. And okay, so what? And I'm going to do it again. I'm going to do it again with x. And let's see, okay, so I'll put the x first, the momentum second, and I'm going to put, now, you know, I could have put this anything, but I'm going to put it where it's going to make my derivation go the fastest. And, okay, so this is, I shouldn't have written it this way, right? I should have done this right. So sorry about that. So this is the that wave function. And this is what we need to know. Okay, how do you project a P into an X bra? Now, as I mentioned several times, cats are not hard, bras are, hopefully, I hope you kind of feel like you got a feel for them, but now hopefully you're looking at that saying, all right, what? You know? Yeah, I mean, okay, where are we at? Oh, okay, not hard. All right, we're figuring, sorry, right, I changed terminology, sorry about that. You get this, but now what the hell is that? All right? It's because, X was always the thing that made it a wave function like you do, and P it's probably not too hard to figure out, but now I put them together. Okay, now to try to figure this sucker out, because, okay, again, you know what pet is. You certainly are okay at resolving identities, and now I've kind of made a little bit of a monster with something that's like, what the hell is that? Okay, here's a way to make it clear. Because I look at this and I'm like, what the, I'm kind of like getting a little lost here, even though I understand what the state is. All right, let's go back to familiar ground. We know what that is. That's a wave function with respect to x. So you're right, and I won't screw that up. That's cosine n pi x over L. It's e to the I kx. It's a helium wave function, all right, not too hard. Well, some of them are hard, but we'll make it an easy one. Okay, let me put all this down again. Oh, look at that, I got myself a delta function. I already just said that delta functions are pretty awesome. This thing that we're trying to figure out, a wave function but with momentum, which you can imagine you haven't seen one before, but it's probably not going to be that hard, which is correct, it's not going to be that hard. Again, we got ourselves a delta function. Left goes first, right goes next, not that it really matters. So now what you got is, right now, to help you understand, the reason I'm doing this is to help you understand what exactly this XP thing is. Look at this. Okay, so now I understand alpha projected into a P draw, projected into P Hilbert space, momentum Hilbert space, is going to be a wave function. It's just not going to have x's, it's going to have p's. And they actually look the same. E to the minus x squared, guess what? It's going to be e to the minus p squared. They really look similar. So this isn't mind-blowing. This is going to turn those new things, this turns these slightly newer things that, again, they're not hard to understand, into that which you are quite familiar. So now I kind of see what this thing's job is. Its job, and it's going to help me figure out what it is, turns p wave functions into x wave functions. Oh, and it won't be hard to turn x wave functions, which again, we have, how many x wave functions have we covered? A bunch of them, right? And you can turn those into p wave functions, and I think on next homework, I'm still trying to decide whether I want you to do this or not. I had you do that on a couple of examples. I actually have some problems written like that. I just didn't know if I was going to apply them or not. Okay, so now we definitely got to figure out what this is, and I see a little bit more about what it does. And this is a neat trick. You're gonna see this a similar trick when we do time dependence, and again, that's going to start. I might even get a little bit into it today. Okay, so we've already done this. Now we also, I elaborated on and on quite a bit about, well, sorry to make it, to do the proof I have to write this. Not that there's not much to this. Okay, so again, your application is good enough. This is kind of battle, but not hard to understand. Okay, but now you may recall that I spent the entire lecture last time defining the momentum operator. The momentum operator's job is to jump out. It's going to jump outside the inner product. Again, that's a weird operator. Operators usually do their work inside, but this doesn't work outside. And that little proof I was just talking about is where you saw that. Due to that step that the book never explained, but I just did, so hopefully it makes sense. Okay, so here you go. Now let me summarize what you've got here. You've got the derivative of x, and again, the little dash, which is just a place-keeping thing, it's nothing, is equal to, I'm rearranging the I and h bar here a little bit. It seems like a lot of the time you see p over h bar in this part of the class, whereas before. But anyway, yeah, so, okay. So I said this, I just brought over IH over there. And heads up, this is it. Yeah, you'll see it? Okay, I tell you what, let's write this as a function. Is it a function of x or a function of p? What do you think? I'm just going to say, so we're trying to solve this, but you're probably looking at this thinking, well, what am I solving? Let's make it easy. Let's write a Diffie cube. We've done a lot of that, so hopefully this isn't going to blow your head off. So I'm going to say that this is a function I'm trying to solve for. now I'm asking, all right, so not too hard, and hopefully you of course know that this is a function. Actually, I always said inner products were numbers, aren't they? Inner products are numbers, but when the number isn't defined, it becomes a function, right? Just like, remember how I told you that there's no such thing as an indefinite integral? An indefinite integral is a definite integral with a nebulous endpoint, with x, capital X, or lowercase x is the endpoint. Okay, so, but now back to task. What do I write? I'll give you two options. It's either x or p, by the way. All right, I think we can narrow it down that much. But what do you think? Is it an x or a p?
X.
It is x, right? Because it's being projected, right? Now, I know bras are really hard to understand. I don't understand them, but I do got that much, right? You're projecting into x space. So yes, it should actually come out the form of an x. Okay, and again, and let me say in words what this is. Okay, this is a function that you take the derivative, the single derivative, and you get the function back times some constants. Anyone want to propose a function that does that?
Yes.
There we go. In case someone didn't hear, over here, someone proposed something, maybe you heard, but anyone over there? I heard the answer, but I heard it over here, so I want to hear it from over there. Yeah, either the something, right? Well, it'd be e to the x. Derivative of e to the x is e to the x. Oh, yeah, but constants come out, so that's going to be I, p, I guess there's a dash, not that it matters. There we go. I'm not writing too small, by the way. I feel like my handwriting is kind of small today. Is that right? I better reach. Yeah. I better look at my notes every now and then. Yeah. There you go. That's. Ta-da. This is what turns a momentum wave function, not that you've seen them, but not that they're hard, into a space wave function. And guess what? What is a little bit probably more practical is you're going to turn wave functions we already know, which of course are x wave functions, into p. It's actually just the complex conjugate of that. So e to the minus I px over h bar. Anyway, getting ahead of myself. So normally I could probably just bow out and say, oh, well, that's that. It probably helps to do a little bit more with it so that it just kind of gets compounded. It turns out that if you think of this as like a wave function, it needs to be normalized. So if you guys, let's look at this deal here. I'm assuming that as much as it's a little, I know you probably should be a little uncomfortable, like what's a wave function with a p in it look like. It's still probably normalized. Now, our wave functions with space should be normalized. We spent quite a bit of time on that. So this thing shouldn't mess with that, right? So there should be, the trait is norm preserving. Another way to put it is that it actually has its own normalization function. So I hope that makes sense. We could actually just not worry about it and then figure this out and renormalize it. That's perfectly fine. And you would get what I'm about to calculate here. Okay, so let's just say that like this is its own wave function. We have a normalization constant. Okay, so now we can figure out what that is. Oh, actually, you know what? Actually, I should have pointed this out. Do you remember when I said the translation operator was 1 minus I k dx? And later we found out that k was p over h bar. I remember that. That was last lecture, I think. I remember that. You ever seen this before? You got kx. Right? Okay. Extra bonus. What's k?
Square root of 2m e over h bar squared.
All right, over there. And it's
2m.
no. Actually, no. You kind of. Why don't you say? Right. Yeah, actually, I did right. No, that was fine, but yeah, you were thinking, you kind of went down the rabbit hole a little too far. It's a wave vector. It's the Fourier wavelength. 2 pi over lambda, the Fourier wavelength. Remember we did that? It's like the beginning of class. Anyway, okay, so maybe you are a little bit more familiar with this than you realize. Okay, anyway, just wanted to point that out, so nothing is too crazy here. Tell you what, let's, we're going to solve, and this is really a minor problem. I'm kind of rather give it to you. I actually, you know, I have one more example here. I'm not very enthusiastic about trying to normalize traveling waves because I don't know that they really are normalizable. Okay, well, let's see. I have I've just taken some weird expression. Well, it's a delta function, but sure. I resolved an identity. I don't feel like making it a delta function yet. Okay, so this could be complex. So this would be n star, that's n. You know, you should know that a complex conjugate times itself is the absolute value. It's not forget everything we've learned. That can come out of the integral. And now I've got a oh, sorry, that doesn't look good now. I'm bothered. And okay, so I've I'm sorry. You know, the little dash again, which are placeholders, they kind of changed the position a little bit, but I've actually done this correct. Now this guy, this is actually the complex conjugate of that guy. It came out positive, but that's just happenstance. The main thing is that this will be negative. Is this the wave function is negative? The complex conjugate is positive. It's just a little bit opposite what you would expect it to do. Okay, that's not weird at all, really. Okay, yeah, you can imagine. I'm going to put this in a very familiar form. IP over h bar. And I've got x prime minus x, which hopefully is very, very familiar to you as from homework number 1, 2 pi delta function. I guess that's x minus x dash minus x. Okay, now you may recall, of course, that, remember I was saying that this is a delta function, so let me, and left minus right, look at that. So let me continue on over here. So obviously, guess what? It's going to be the square root of 1 over the square root of 2 pi. 2 pi h, yeah, 2 pi h bar. Wait 1 second. No. So, yeah, there's an extra h bar there. Actually, yeah, it's not, to conform to the definition. Sorry, I should have pulled out that first homework. Yeah, there's normally that constant in the definition of the delta function, a constant would be there. So if it's there, then it's going to be like this in the answer. I hopefully that conforms. Remember your very first homework problem. Hopefully it conforms to that. I'm going to say that it does. I don't quite remember. Okay, so what we got? So this is 1. 2 pi h bar squared, and so therefore, I'm just going to tell you n, of course, is 1 over 2 pi h bar. All right, so therefore, depending on which way you're converting, whether you're turning momentum. Oh, sorry, this is handwriting, so we decided to stop working. H bar, minus. So that would be going from x to p. So that's kind of what you're going to want to do more than not. You have to have p. Writing the same thing. You have to have p to begin with and are converting to x. It's just a complex conjugate. And we've already, this is actually what we already solved. Yeah, there we go. Yeah. So there you go. So then let me give you the punch, the take home. I've already written how to turn a momentum wave function to a space wave function. Again, that's like kind of weird because it's like, where does the space wave function come from? Well, it would come from this. You probably would have calculated it this way. So here's our factor. So you see our normalization preserving deal. And this is a Fourier transform. Just like, again, harking back to the first homework, Fourier transforms. Fourier transforms are pretty awesome. So not only can you do a lot of signal analysis with this, there are certain quantum mechanical types of quantum mechanics that do tons of Fourier transforms. I'm going to show you a way to calculate wave functions. I don't think I've shown you. I can't remember what I've shown you, what I haven't shown you yet. God, good. At some point, did I show you the finite difference method? I have not shown you that, right? Okay. So, yeah, I meant to do it sooner, but I think I just kind of let time get away from me. At some point, I'm going to show you how to solve wave functions for any potential surface, any one whatsoever. One's called the finite difference method. I find that very useful. That's for, I should have done it by now. We've kind of already covered the material for that. But another one's called the split operator method. The split operator method, it's a way to evolve wave functions in time. And now this is all numerical, it's all MATLAB. And you're gonna get like a particle in a box, you're gonna put it on a parabola. Notice that particle in boxes don't belong on parabola, so it's gonna bounce back. You're gonna calculate this and you're gonna visualize it. You're gonna watch the wave function bounce back and forth forever and ever. It's kind of cool. And that uses Fourier transforms. You're also then going to be able to calculate the wave functions of the Hamiltonian that way. Anyway, so you're going to see this again. Really useful stuff. And there's also, on my website, and I sent you this already, right? My little MATLAB deal. Introduction to MATLAB. Well, if you got past the first chapter or two where I just told you like x equals 5 and here's a for loop, eventually some of the chapters I get into Fourier transforms, Fourier filtering, and how Fourier transforms work. I even have a paper just got published a few 2 or 3 months ago, and it was about Fourier analysis of, guess what, X-ray diffraction patterns. So this is an important thing to know about. Okay, now last bit on your homework. Imagine our brains work very differently, more correctly, and we never thought of the world around us in terms of space, but momentum, which would be like a derivative filter. Actually, I saw this talk on optics right before the semester began. And so there's these things called differential optics. It's like, all right, any of you ever do any picture filtering where it's like does edge detection? Like it kind of like makes something look embossed. You know what I mean? Just like I take my picture right, and then you don't see all these features, you just see the edges of where I stand out. You know what I mean? Yeah, so that's a derivative filter. Google it. But anyway, So if we looked out of the world through derivative filters, and we only did things in terms of momentum, well, now what's x? X is not x anymore. Just like p is the derivative of x, well, guess what? So what's x in the land of p? And this is already on your homework. You've already seen it. You know it's just the derivative with respect to p, but let's prove it. And the point of that problem is that if you lived in a world of momentum as opposed to space, the Schrodinger equation itself actually could be easier to solve. When we live in a world of x, and the momentum operator, unfortunately, it's the momentum operator squared as kinetic energy. And that means that you're solving a second order differential equation. Schrodinger equation is inherently a second order differential equation, which sucks. Okay, but on your problem, when momentum just isn't anything, it just sits there, just p squared is p squared, just like x squared is x squared. X didn't have to do anything. In the world of p, neither does p. But x by itself is just a single derivative. And a first order differential equation is way the hell easier to solve than a second order. So anyway, that's the value. So, yeah, thank you.